Good afternoon, everyone, and welcome to another Big Data London webinar. Today, we're looking at what graph-powered contact tracing can teach business. So I'm Andy Steed, Content Director of Big Data London, and I'm joined today by Rick from Neo4j. Hi, Rick.
Hey, guys.
So these sessions are designed to be interactive, so please send in your questions at any point using the questions function, and I'll endeavour to ask as many as I possibly can at the end of the session when we've dedicated a little bit of time to Q&A. So a little note of housekeeping. If you lose the stream at any point, you shouldn't, but if you do, just hit refresh in your browser and you'll jump straight back in. However, without further ado, I'd like to pass it over to our featured presenter today. Over to you, Rick.
Super. Well, thank you so much for giving me the opportunity. Appreciate it. And I'll start sharing my screen and take you through a couple of slides first, and then we'll do a little bit of a demo as well. Hopefully that'll be interesting for you. Just hide this little bar over there. All right, guys, let's go. So we'll talk a little bit about contact tracing, right? Because it's a really interesting use case, and there's a lot of lessons to be learned there. But before we do, I'd like to give you a little bit of an intro to Neo4j. I work for a company called Neo4j. This is a Swedish-American company. We're originally from Malmö, Sweden. We started out as an open source project back in 2001. That's when everything 4J was still very, very hip. But incorporated in 2009, and then really took off 2011, 2012. And I've been with the company since 2012. So quite a ride, I must say. And yeah, it's really a company that kind of pioneered the graph space, the graph technology space, and as a consequence, we have a lot of experience with that. We have a lot of staff, a lot of specialist staff, and a lot of great customers, great partners that do amazing things with graph technology. And when if you're not familiar with it, I guess a little bit of context here would be useful. End of the 70s, early 80s, someone invented this wonderful piece of technology called a relational database. It's dominated the industry for 40 years, and it's basically extremely good at storing and retrieving data in a structured way. But there's kind of two, question marks that have been following around this wonderful technology called relational databases for all of those decades. And the first one of those has been volume. What do you do with volume? What happens when those beautiful tables start filling up and start containing millions or billions of rows? How do you get data in? How do you get data out? And as a consequence, there's been a lot of focus in the past decade on creating something called big data technology that allows you to aggregate and filter data much more efficiently at scale, right? I mean, things like MongoDB or Cassandra or even DynamoDB or something like that. These are technologies that are excellent for working with large volumes of data. But there's also a second, kind of challenge in the relational world, which is everything to do with connections, with relationships, right? In a relational world, those are typically formalized as join operations, right? So joins between tables, and guess what? Those can get very expensive. They can get very cumbersome, difficult to understand, difficult to run, difficult to model. All of those types of things, and that's where the graph database space has kind of emerged from. We really are a solution to making sure that data that contains lots and lots of connections, lots of relationships, can be efficiently queried, can be efficiently manipulated, right? And that's because the fundamental data model that underpins graph databases is radically different from the relational data model, right? In a relational database model, you work with tables, right? Tables that contain columns and rows. In a graph data model, you work with little balls and arrows, nodes and relationships, right? And that's what we call the labeled property graph, right? It's similar in many ways to a relational system, but it's very different in the sense that the relationships between the different entities, between an employee, a company, and a city, are an explicit part of the data model, right? So they're not calculated anymore at query time. No, you actually write them down as an explicit part of the data model at write time. At write time, I'm going to formalize, I'm going to persist the fact that a particular employee of a company is a CEO of that company, or that that particular company is located in a particular city. I'm going to formalize that, I'm going to persist that. It's going to be part of my data model. And as a consequence, at query time, I'm going to spend a lot less time trying to calculate that, right? And one of the great things about that is that this data model, right, balls and arrows, nodes and relationships, is super, super high fidelity. You know, it's very easy for people to understand, because people, when they describe their problems, you know, they very often start to draw little bulbs and arrows, right? That's what they do, right? So in a movie data model, you would draw something like that, and the next thing you draw would be something like that, and you know, you're starting to look a little bit more like a database data model, right? You can see this happening, right? It's really, really similar, and it's a one-to-one mapping between what ends up being stored in the database and what the original domain owner actually drew on his whiteboard or her whiteboard, right? So there's a lot of advantages to that, you know, in terms of modeling, but also, as you will find out later, or hopefully you will see later, there's a lot of advantages as well in terms of speed, right? And that's just because those join operations that we had to do on query time, time and time again in the relational database, now we can just do them, we can run them once, we persist the result, and we can just retrieve that result whenever we need it at query time very, very efficiently, right? So this is really the core of what we call native graph technology, right? Where graph databases and all the tools around it, you know, the integration tools, the development tools, the analytical tools, the discovery and visualization tools, all of these things come together in a native graph technology platform, right? And we think that's really important because, you know, many of today's really, really interesting and transformative IT applications kind of center around this concept of a connected data infrastructure, right? I mean, whether you're talking about hyper-personalization with recommendation engines, or data lineage application in a data integration system, or machine learning and AI, you know, all of these massively transformative applications really are based on, you know, a graph data model, right? So we think there's a lot of potential for this and a lot of interest in this going forward, which is obviously fueling our growth, right? Now, enough said about that. We were going to talk a little bit about how we use graphs for this extremely interesting and relevant topic these days called contact tracing, right? And then what we can learn from that as a business organization, right? And in order to kind of go into that, I'd like to give you a little bit more context. I mean, contact tracing has been in the news in every country, every newspaper these days. But what do we really mean with that, right? Well, I guess the most important thing that I at least have understood to be the relevance here is the fact that, you know, we've got this huge pandemic going on. During spring, most countries had no other choice but to isolate and lock down part of their societies in order to kind of get the pandemic under control, right? And that basically meant that a lot of people that were perfectly healthy had to isolate themselves, had to go into quarantine, right? And obviously, that's a huge cost to pay for a situation like this. It's an unavoidable cost at the time, but you know, it was a very, very big cost. What every society, you know, UK, my own society, Belgium, France, Germany, you know, every country is looking at this, is trying to achieve now is to figure out a way that when we hit a second wave of this pandemic, which is unfortunately quite likely, right, that we don't need to quarantine or isolate the healthy, but that we just need to isolate or quarantine the sick, right? That's what this is all about, and this is a very, very complicated issue, right? And I don't mean to claim or to say that we have all the answers to this, because there's so many different things to consider here, so many different options that we are considering and that people are looking at, and I'm just going to highlight a couple of those, right? But the principle is always quite simple, right? It basically means that whenever you visit something, whenever you are in touch with other people, whenever you participate in an event, whenever you go to a restaurant or a pub or whatever you do, someone or something is going to try and keep a registry of this, is going to try and trace this, right? And make sure that if something might go wrong in your immediate environment, that there would be a way of either cutting the chain, right, making sure that the spread of the pandemic doesn't continue broader than than what it already has, or that we could literally analyze the entire reach of the population to see what is going on there. So that basically leaves us with two different types of contact tracing, right? Which I guess not everyone is equally interested in. They have massive issues on both sides. They can be hugely wrongly implemented in all cases. But the basic question is, do we want to implement some kind of a centralized contact tracing system, or do we want to decentralize that system, right? And I guess most people have heard about, there's some of the plans that the UK, but also Germany and other countries have put in place, where at the local level, at the individual's level, it's actually very likely to be a very decentralized and privacy conscious system. And at the central level, there might be some trade-offs to be made. It might be a little bit less privacy aware, but it would be more protected, right? In any case, I think there's a case for both. The decentralized one allows you to break the chain, right? It allows you to break the spreading of the pandemic. The centralized system allows you to understand the spreading of the pandemic, and also to potentially, apply different types of policies to it, right? Lockdown or other, right? So there's a lot of trade-offs here, and again, no opinions on my side on what would be right or wrong here, but it's pretty clear that in both cases, this contact tracing system would need to be based on some kind of a graph data model, right? It would be very much about, person contacts on other person, contacts another person, contacts another person. I mean, it's all about the relationships. And this is not new, right? This is something that has been around for a very long time. It's been studied, in Ebola, in animal diseases. Lots of research has gone into this, and lots of analytical work has gone into this. And I think it's fair to say that the scientists out there, they have a reasonable understanding on how this type of spreading could work, right? It's very difficult to control it, but they do understand how it works, right? So the history of what I'm going to tell you next is that I personally got involved with this earlier this spring. There are a lot of people in the graph community, in the Neo4j open source community, that got really interested in this, and that really started to build a bunch of tools and a bunch of examples that were highlighting, how graphs could help with the current pandemic. Some of that has been very, very academic and very research oriented. If you go to covidgraph.org, it's one of those sites that I think is a fantastic example of bringing together people from lots of different areas of expertise to kind of accelerate the research space around COVID. Right, there's been a lot of academic work going on there, very interesting work there. But I personally got involved with this this contact tracing model to kind of make people understand that graphs have some really interesting value to add to better understand how that traceability model might work. And so what I'm going to show you in the next couple of minutes here is an example of that. It's an example based on a realistic, but obviously not production worthy contact tracing model, right? And to do that, what I've created is I've created a synthetic data set, right? So no real names or real places are going to be shared during the rest of this presentation. But you can see that it's actually quite simple, right? You have a person who visits a place, right? The visits themselves, they're actually a little bit redundantly stored in this model, right? Because they're also reified into visit nodes, right? A person performs a visit is located at a place, right? So that's kind of like the simple data model that we've got here in the synthetic data set that we created. And as a consequence, you can also argue that if a person visits a place, from a time stamp to another time stamp, right? So at a particular point in time, then realistically, you can also assume that they meet each other, right? So a person meets a person, right? And this is the basic data model that we'll be working with. This type of a triangle, right? And it's actually very similar, as you will see later on, to other use cases, graph use cases that use very similar data models, right? Now, the one thing that we can do, obviously, once we've got a data model like this, is we can query it, right? We can try to understand it. We can say, okay, how are two people, of different health statuses? One of them is healthy, one of them is sick. How do they connect to each other? What are the paths that are running across this network of people and places that connect people? But actually, quite a big part of what we've been doing here is actually to apply a different type of analysis on this based on graph data science algorithms, right? And graph data science is I guess a little bit of a new activity that was created a couple of years ago. On top of this new application of graph databases and graph data technology in general, to really run some of the most important graph algorithms, right, on top of graph data models, and to see what we can learn there, what new insights we can learn there. And I'll show you a couple of those that are really interesting. The first one that I'll show you a little bit later on is something called Pagerank. Right, Pagerank. I'm willing to bet that all of you have used this today, Pagerank. Why? Because this is the graph algorithm that underpins the Google search engine. Right, and I don't know what your age is. I'm 46 years old, and I remember the days before Google had a search engine with Lycos and Alta Vista and all of those crappy search engines that dominated the internet at the end of the 90s. Well, Google completely overhauled that space by implementing a different type of search engine based on a graph algorithm called PageRank, right? What PageRank does is it looks at the structure of the connections between web pages, right, to understand which web pages are likely to be more important, right? Because they refer to each other, they are linked to one another, right? Guess what? We can apply that to contact tracing. We can look at contact tracing and see, okay, who in this contact tracing graph has been in touch with other people the most, who has actually got the highest PageRank score. And as a consequence, we can see, okay, that person is probably really important in this contact tracing graph, or that place is really, really important in this contact tracing graph. We need to take some active measures there, right? Very interesting algorithm and very easy to run that on top of a graph database using a graph data science library, as you will see a little bit later on. Another graph data science activity that I want to show you a little bit later on is something we call betweenness scoring. Right, and betweenness scoring is really interesting because in every graph you're going to find that some parts of the network are connected more to each other than other parts of the network, right? So there's like these little communities in any kind of graph network, right? Now, between those communities, there's usually a couple of people or structural elements that connect those communities, that are between those communities, right? And these things, or these people, or these places are hugely interesting, right? Because they can tell us something about what might happen to the structure that we are looking at over time. How likely is something to spread from one community to another community based on their betweenness, right? Really interesting metric in the context of contact tracing. But also, in other cases, in other domains, betweenness can be super, super interesting. And I already mentioned these communities that form inside many graph networks. Well, guess what? There's algorithms for detecting these communities, right? To understand which parts of the graph belong together. Right, and again, same thing for contact tracing, right? It's very, very useful to understand which parts of a network belong together, because that will allow us to basically take appropriate measures when we need to, for example, go into a lockdown or do something else there. I'll give you a quick demonstration here of what this synthetic data set looks like, right? I've got a database running over here, an Neo4j database running over here. I'm on an average laptop, guys, so I'm not running any supercomputers here. This is a very simple database. It's got 10,000 nodes in there, 15,000 relationships in there. And if I open that up over here, then you will see, that this is what it looks like, right? So I've got people in here, right? I've got places, right? I've got visits. And obviously, if I go back here to my people, I can explore this. I can take a look at, okay, so this particular person, Janita Kettner, who has that person been in touch with, or which places has she visited, and who else visited those places. I can immediately kind of explore this and see what's going on. I can write queries, obviously, right? So there's a query language that comes with a graph database, right? You can see a very simple one over here, right, where you can basically say, okay, I'm going to match for a node that has a label, a person label. I'm going to return those nodes, and I'm going to limit it to the first 25 results, right? I can basically do this a little bit more extensively and say, okay, I'm not only looking at the nodes, I'm also looking at the connections, right? So give me the nodes and their connections, right? So, and this is how I basically draw out a pattern that I can match for. Right, so this is how that works. Very simple. I can make this as very complicated as well, but I'm just giving you a feel for what that looks like. And there's also a visualization environment that comes with Neo4j. This is something we call Neo4j Bloom, where you can actually wrap those queries, wrap those technical database interactions into an application. So here I can say, okay, give me 10 people, give me 10 persons, right? Okay, I only need to write this over here, right? I don't need to write a query. I can just say, give me 10 query, 10 people. Okay, and then I can say, okay, show me this one. What's going on there, right? I'm going to hide everything else. I'm going to expand this, right? And all of a sudden I can start looking at all the details of this particular person that has been going on here, right? So that's how that kind of works. It's a very simple way of interacting with it. And obviously I can also run graph data science algorithms on top of that with a graph data science library that is installed on top of Neo4j, right? So there's if you look here, there's a plugin that's been installed here, a graph data science library, and this allows me to run graph data science algorithms very, very easily. Right? Cool. That's kind of what the standard contact tracing capability looks like. Now, what I'd like to do next is to highlight how this is actually quite relevant for a couple of business applications. You know, why does that mean business, so to speak? You know, why is that useful here? Well, the way I kind of think about that is something that I have to do, or that I get the chance of doing very often with our clients, which is to try and think about, okay, what is the most efficient way of solving a particular business problem, right? We call this the graph problem. What we basically are trying to solve for here is in many IT oriented or business oriented problems, there's more than one way of solving things. There's always, different ways of doing things. There's always different way of getting to a solution, right? But what we've all kind of seen, I guess, is that when there are more than one potential solution, there's usually one solution that kind of stands out as being most appropriate, right? And I guess what we're trying to figure out here is, are there other business problems where you can basically say, okay, it's not just the contact tracing thing that's a clear graph problem, but other problems are actually very, very suitable for graph solutions as well, right? I think we can all say that, first, the contact tracing use case is a really clear graph problem, right? The domain model is all about the relationship. It's all about the links between people and places, right? The graph queries that we are running on top of the graph, like for example, to try and understand the links between two people, to try and understand the links between sick people and healthy people, to try and understand the links between different places. They're all about understanding the links, right? So the graph queries are very, very interesting here. They're easy to use, they're fast, they're quick, quick to run and quick to customize. And on top of that, the graph algorithms, the analytics are actually yielding really interesting results without us having to actually know the domain. I can immediately see, okay, these parts of the graph are more interesting based on their Pagerank score, their Betweenness score, or their community affiliations, right? So I think it's pretty safe to say that contact tracing is a clear graph problem. So which other business problems are also graph problems? Right now, obviously, I can sit back here and claim that these use cases, which we've seen with so many different clients, are clear graph problems, right? But I'd like to illustrate that. I'd like to show that to you guys, right? Real-time recommendations. How do I the typical Amazon use case, right? People that have bought this have also bought that, right? That's connections between people, products, and other people and other products, right? Fraud detection, things like crash for cash schemes in the insurance sector, right? This is a typical type of fraud use case. network and IT operations, telecom operators need to manage networks. Well, wouldn't it help if they actually could represent their networks as networks, right? To understand, for example, where root causes of defects are, or where potential impacts would be of failures in the network or something like that. Master data management, there's all a lot of talk about data governance these days, right? Making sure that the right people have the right types of access to the right types of data. Well, we need to govern that links between the different data sources as well, right? And that's where making those links into a graph is really, really useful. Knowledge graphs, understanding how different pieces of knowledge can link together. The covidgraph.org is a great example of this. And the last one, identity and access management, managing access. For decades, it has been structured into hierarchical structures, like LDAP trees or something like that. In matter of fact, lots of people are starting to move those access control definitions into graph structures, because that's a much better way to reflect their actual organization structures these days, right? So all of these things could be graph problems, right? But I'd like to show you how that actually really, really maps to the contact tracing use case, right? So I'll give you two scenarios, two illustrations here to kind of get your creative juices flowing, I would say. The first case I'm going to try and illustrate is how contact tracing is extremely similar to product recommendation systems, right? And I recommend that you purchase this product, yeah, right? Because another person has purchased a similar product or something like that. It's very similar to us trying to highlight and find potential infection points in the pandemic, right? And another case that I'd like to illustrate to you is the similarities between contact tracing and VAT fraud detection systems. And I'd like to get into that. I'd like to show you that. And basically, the point I'm going to try and make is, you know what? They're both graphs. They're both graph queries, and you're going to find lots of similarities between them. So let's get into that, right? So the first thing that I'm going to try and show here is how the contact tracing data model, right, which is on the left-hand side here, is extremely similar to a product recommendation system that you would find on the right-hand side here, right? Instead of having people visiting places, you're going to find persons or people purchasing products, right? It's a very, very similar triangle that we're looking at here, right? So this thing here is basically going to get a one-on-one translation into that thing over here. Let me show you that. Let me show you how that works in the real world. I just need to go back over here and open my Neo4j browser here. Now, what I've got here right now is just one database running, the Neo4j default database running. What I'm going to set up here now is I'm going to create. Need to run this query. It takes a couple of seconds. I need to run this query that will basically create another database for us to play around with and to illustrate the similarities with the contact tracing use case. You can see all the queries happening here, right? I think it's almost done. Let me see. Yeah, all right. It's making good progress. It's a little bit slower than when I'm not presenting on the web, it seems. I hope this is coming across well. All right, that's done. And all of a sudden now I don't have, I have 4 databases running here, or actually 3, system database and 2 others, right? So this is still the database that I showed you earlier, right? With the person nodes, the places, right? That's what I showed you earlier. But now I've got this recommendation data set over here, right? Which is similar, right? But it's actually quite different, right? So it's got the people, right? People that visit places, but it doesn't have any of the meeting relationships, right? Next thing I'm going to do here is I'm going to transform this data set, right, into a product recommendation graph, right? So all I need to do there is run this query here, right? Basically what this does is it grabs all the visits and makes them into purchases, right? And then it grabs all the places, right? And it makes them into products, right? That's the essential transformation that it's going to do, right? But the structure, right, of the data set is exactly going to be the same as what I had earlier, right? The links between the different people and places are just going to be replaced by links between people and purchases, right? So I still got my people here, right? And now all of a sudden they've purchased a product, right, through this purchase over here. There's another person here that has bought that product as well, and that person has bought another product, right? You can see this, the structure is exactly the same, right? And now what I can do here is, now that I've transformed the structure from a contact tracing graph into a product recommendation graph, is I can run some queries on it, right? So for example, this query here, right, which is a very simple query, right, which is looking for a path. It's looking for a path between a person that has purchased a product, right? That product has been purchased by another person as well, right? And that other person has actually bought another product, right? So all I'm going to do, if I run this query, what I'm going to get is this type of a recommendation here, right? Because this person here has bought a product, right? Oh, sorry, that was a stupid thing to do. Let me rerun the query. Sorry, that was a stupid thing to do. Right, so here, this person here, Marjorie, she's bought a product. She's also bought another product, and these other people here have also bought that product. Now, all of these other people here might be interested in this product as well, wouldn't they? Right, so this is the start of a very simple recommendation query, right? We can make this a little bit more complicated by saying, okay, I don't want the person to have bought one product, right? I actually want them to have bought a second product as well, right? So then what you get is a little bit more of a stronger recommendation, right? You have this guy here who has bought 2 products, right? So as a consequence, that means that he must have some kind of a strong feeling about these products, and these other people have bought other products that they might have been good recommendations here as well. Right, so that's kind of the point I wanted to make here. The structure of these 2 graphs, of the contact tracing graph and the product recommendation graph, is identical. Nothing has changed there, right? But the queries are actually very similar as well, but they are completely different domains. We're not trying to find spreads in a pandemic. Really, what we want to analyze here is what next product might I be recommending to a potential customer. That was the first point I wanted to make, right? So I'm going to basically do that for another example, right? I'm going to try and illustrate to you that if I have a contact tracing model here at the top, right, where a person meets another person, right? Remember, that's the part of the data model that I put into the original synthetic data sets, right? So because a person has visited a place at the same time as another person, we're going to infer that these people have met, right? And as a consequence, this is part of the data model, person meets person, right? Now, guess what? In many fraud detection systems, these types of recursive relationships are really interesting, right? For example, here, the example that I'm going to try and illustrate this with is a VAT fraud detection model, right? If I replace the people with companies, right, and replace the meeting relationships with invoicing relationships, then it's not very difficult to imagine that what we would want to find are these sorry, my screen isn't following here, but what we want to find here are these VAT carousels, right? Where a company invoices a company, invoices a company, invoices a company, and goes back to the first company, right? Because they want to dodge the VAT to be paid to the government, right? Value added tax, that means that, in every step of the value addition process, you're supposed to pay a little bit of taxes on it, right? And at the end of the day, the end consumer is supposed to pay the entire VAT. But literally, if the companies keep on invoicing each other, then that means that there's some kind of missing trader, as people call it, right? There's something missing here. The required tax is not going to get paid, right? So let's explore that a little bit, right? Because again, there's similarities here with the contact tracing model, right? So I'm going to switch to a different database, the fraud detection database here, right? And then I'm going to convert that database to a VAT fraud detection graph. All I need to do for that is I need to convert, right, all the people into companies, and I need to convert all the meeting relationships into invoicing relationships, right? So that's what I'm doing here. All of a sudden, right, I don't have, I still have a person showing up here, but at the end of the day, the bulk of the companies are now, the name of that particular person, limited or incorporated or whatever, right? And instead of having the meeting relationship, I now have the invoicing relationship, right? It's right there, right? So company meets person meets person has been replaced by company invoices other company, right? Again, the structure of the database, right? The links and then how they are linked to each other and stuff like that, all of that is identical. Nothing has changed here at all, right? It's just that the domain is different, right? We're not talking about meetings, we're talking about invoicing, right? So that's been done now. The conversion has been done. So now I can show you a couple of super simple fraud detection queries here. Like for example, this one here, right? I'm looking for a path, right, of a company that invoices another company, which then goes back and invoices the original company, right? So this is what it looks like, right? It's very simple. This is the most basic, potentially suspect query. That's easy in any data platform, but what happens if you have longer chains, right? If you have 4 or 5 companies in a carousel like that? Or what happens if you have 20 companies in a chain like that, right? So this is where, in the contact tracing graph, this would be person meets person meets person meet person meet person meet person, right? This would be the circular meeting structure. In this case, we're looking at the invoices, right? But this thing here, what you're looking at, would be a prime suspect for any kind of a tax investigator to look into, right? Because this is not a normal structure. This is not what it's supposed to be like, right? At the end of the day, someone is supposed to pay the VAT, and that's usually going to be the end user, right? That buys something in the shop, right? So this is how this thing is, again, very similar to the contact tracing use case, but we can use the power of the graph not to find, meeting relationships, but by finding fraudulent invoicing relationships. So again, this is what we can learn from that. We can use the graph technology to do something a little bit more interesting that is more relevant to what I would call the traditional business use cases. Right. There's a lot more to be said about that. I've written a bunch of blog posts about this. All of the code that you've just seen is all on GitHub, and you can play around with that if you're interested. But maybe this is a good time for me to kind of switch back and offer some conclusions, and then we can do some Q&A, right? So what I've tried to do in today's webinar is really to tell you a tale of three graph problems, right? To illustrate to you how contact tracing as one of the, I would say one of the hottest applications out there these days. Definitely a graph application, right? There's a lot of graph modeling that's very applicable there, a lot of graph algorithms that's very applicable there, but it's extremely similar to these other two graph problems called product recommendations and VAT fraud detection, right? Why? Because they both, or all of them, have a lot of connectivity between the different entities, right? There's a lot of links between the different entities that we have in the data model. They all require some kind of deep querying, recursive querying or variable length querying into the graph to understand the connectivity and to derive new insights, right? And all three of them can benefit from our algorithms, right? From Pagerank, from Betweenness scoring, from community detection to provide new kinds of insights, right? In a contact tracing world, we would like to be interested. We might be interested in similarities in communities of patients, right? But in a recommendation graph, I would be equally interested in communities of products, things that are similar to one another, and that I could potentially offer up as replacement products if one of them was not in stock, for example. Those types of things. All three of these graph problems are pretty clearly going to be benefiting from a graph infrastructure like the one that I demonstrated to you a little bit earlier today. So I'm hoping that was useful. I'm hoping that you guys thought this was a useful summary. Happy to discuss some more. You can find me online and I'll be happy to share more examples if that would be useful. But for now, Andy, I don't know if you had any questions while I was talking, but that's what I wanted to share today.
Perfect. Yeah, I have a couple of questions for you.
Super.
Is it okay if we go back to the video where Rick?
Absolutely.
And before I ask any questions though, I just wanted to make everybody aware that, or people, especially people who joined a little late, maybe, that this session is available on demand to view almost instantly after we've finished. So you can go back in, you can have a look at some of those demos again, and rewind and fast forward, etc. If you would like to. Secondly, obviously, thank you very much, Rick, for that very, very interesting explanation of contact tracing. I did have some questions actually, and there's some questions coming from the viewers as well that we'll try and get to as well. I suppose my first one really is, there's probably people who've tuned in today who are considering using this, considering maybe a graph technology to help them, and more generally. So, first up, I guess, is there any sort of barriers that people face typically, and how do they get over them and drive real value from this? Is there anything you see typically in the early stages of people trying to adopt this technology?
Of course. Lots of barriers, actually. No, I mean, I'd be lying if I said that this was all completely fully baked for everyone, right? But I guess, the biggest challenge that I find is that, you know, most of us have been schooled, have been drilled, have been taught their third normal form and relational database technology, till they're blue in the face. They're very much drilled that way, and I guess. Um, Graph technology, while conceptually it's actually quite similar, right? But the parameters are very different, right? I mean, people sometimes ask me, does Neo4j scale to blah blah blah? And I'm like, that's the wrong question, because in a relational world, data size or data set size is a very important parameter, right? Because the joins between tables are going to get more difficult if your tables become longer. It's pretty simple, right? In a graph, it doesn't work that way, right? Because you work with something we call, graph locality. The speed of a query is not determined by the data set size. It's actually determined by the result set size, by how much of the graph you want to explore. Right. So as a consequence, the parameters of what you're doing are very different, and as a consequence, you kind of have to unlearn what you've learned learned before in the relational world before you're going to get very comfortable with graph technology. So, the most important thing there, I think, is take the time to learn. Don't be surprised if it doesn't work from the first time. Call in an expert, either on the community. Neo4j is still very much an open source company. There's a big community out there of people that want to help. Or, if you want to go quickly, pay someone. There's plenty of graph experts out there that have done this before and that can help you. But there are some hurdles. You have to unlearn before you can learn again. You know what I mean? And that's the biggest one in my book.
Yeah, no, I think it's a really good analogy, actually. Yeah, and I mean, I suppose my second part of that question, I think you kind of answered it. I mean, again, like kind of managers and team leaders who are watching this, is there a kind of person that they should be thinking about hiring? I know hiring's difficult at the moment, but what sort of skills does somebody who's going to be really helpful at this kind of need, in your opinion, kind of thing? Who should they be looking at down the line?
Yeah, well, I mean, obviously, I personally think that any good SQL DBA could be a good graph specialist. I have no doubt about that. Obviously, you have to be willing to do it. You have to be willing to unlearn and relearn. You know what I mean? And that can there's a little bit of a mental jump that you need to be willing to make there. But I would say, if you're familiar with open source databases or with SQL, things like MySQL or MariaDB or something like that, and you're familiar with declarative query languages like SQL, you're going to have a very, very easy time getting started with Neo4j. It's actually simpler than most databases because it's more natural. The data model is actually just more natural for most people. So as a consequence, I would argue, just look for a good data specialist, and you're going to be fine. It's not rocket science. It just requires you to unlearn and relearn a little bit.
Okay, thank you. Yeah, there's a good question just come in. Actually, about the use cases that you went over, and how they're relatively new. That 5 years ago people wouldn't have used this kind of technology. Like you said in your presentation, they would have been using more classic big data or relational databases technology. Is there anything that you think's on the horizon that in the future will be a use case for graph database, which perhaps we're not mentioning at the moment?
Well, I mean, so let me answer that in two parts, if you don't mind. I think the first part is we're going to do everything we're already doing today, but we're doing it in batch. We're going to do it in real time, right? That I think, whether it's a recommendation system or a fraud detection system or an anomaly detection system or an access control system or, well, you name it, lots of different systems that currently we actually have to treat them as batch oriented system. We run something overnight and in the morning it's there and it'll work for a day. Those types of things, we see that a lot today because of some of the limitations that we have in our traditional data infrastructure, right? That's why they're batch oriented, right? And I think that many of those applications are going to have real-time requirements, and I don't want to go into specifics there, but I think lots of them are going to get real-time requirements. And the only way to do that is by getting rid of those join operations. You just need to get a different way of dealing with join operations because you can't do those in real time anymore, right? So as a consequence, I think that's the first part of my answer to that question. The second part, it's at risk of being just another person who says this, but it's artificial intelligence. It's all about making sure that the systems that we use to train and to learn and to derive new insights from the data that we generate, that they become smarter. And one of the ways that they can become smarter is if they have more context, if they have more relationships to the links, to other systems, to other parameters around them. And I think what we are starting to see, and what we are, reason why we're also developing a lot of software around this, is that many of those AI systems are using graph data models, and as a consequence, they're going to start really requiring graph infrastructures, because if they don't have a graph infrastructure, that means that they are constantly going to have to switch back and forth between a columnar or a tabular data format into graph and back, and they're just going to spend too much time doing that transformation. So I am a firm believer that we're still at the early days of graph adoption, and AI is going to be the big one for us.
Okay. Oh, perfect. Well, if it could fix COVID as well in the meantime, that would be brilliant as well.
Working on it.
Yeah, obviously maybe setting it too hard a target there. So, it's very interesting.
I mentioned it a couple of times. Sorry, Andy, to interrupt you, but I mentioned it a couple of times during my talk. If there's one website that I think people should take a look at, especially if you're in pharma or biotech or those types of domains, it's covidgraph.org, right? And the reason why I say that is because, half jokingly we're saying this, that we'll fix the pandemic, but one of the ways that people are trying to provide cures to COVID is by reutilizing things that we already know, right? So knowledge graphs, right? Not just about viruses, but about molecules, about existing drugs, about existing treatments, those types of things. Bringing those together is actually the best chance we have of coming up with a suitable cure quickly, right? I was talking to a guy from J&J from one of the big pharma companies on one of my bike rides over the weekend. But what they are trying to do is they're trying to reuse their vaccine platform for a COVID vaccine. Right? They're not going to develop that from scratch, because if they would have to, it means 2025.
Yes. Yeah.
Right. So they need to try and reuse stuff that they already have, and covidgraph.org is a great example of that. It's really, really interesting.
Perfect. Well, I'd also like to mention another couple of links in the attachments. In the bottom left-hand corner, there's some further links from Rick there, and you might want to check them out as well if you've enjoyed today's presentation, as I have. But I think we've actually unfortunately run out of time, so I'm gonna wave goodbye to everybody and say goodbye. But first, I'd like to say a big thank you to Rick. Really enjoyed that. Enjoyed the chat afterwards as well. No, that was great. So from us again, it's goodbye. So thanks, Rick. Thanks everybody at home, and we'll see you all soon. Thank you. Bye bye.